No.
Okay, so we're live now.
Oh.
Is this your?
Yeah. Oh.
Zhiyun, is it your slides?
Yes.
Okay.
Can you see my screen?
Yes. So I'll just give a quick intro. I'll do just 1 minute. So hello everyone. I actually don't see. I see. Okay, there's people in the audience now. Okay. So I'm Ariel Ortiz Bové, and I'll be keeping time. And so without further ado, so that we don't waste any time, the first presenter is Zhiyun Li, who's a PhD candidate at Cornell, and she's going to talk about the timing of relevant weather conditions in agriculture. So Zhiyun, the time is yours.
Oh, okay. Hello, everyone. Thank you so much for coming to our session on climate change and agriculture. My name is Zhiyun, and I'm a PhD candidate in environmental economics. I'm very happy to be the first person to present in this session. The title of our paper is on the timing of relevant weather conditions in agriculture. This paper is co-authored with Professor Ariel Ortiz Bové. In climate economics literature, there are growing studies looking at the impact of weather shocks on economic outcomes. There's an empirical challenge in this literature is that weather data are often of higher frequency, for example, at the daily level, and the economic data are often of lower frequency, for example, like at the annual level. So to estimate the impact of weather shock, you need to aggregate the weather data temporally. Agriculture economists often have necessary background for the timing period. However, for example, they use monthly or annual average, or a season ranging from April to September to study the impact of weather shock on agriculture outcome. However, sometimes the relevant season is not that obvious, especially when you are dealing with aggregate agriculture outcomes. For example, like total factor productivity and GDP. To our knowledge, there's little guidance in the literature about how to choose the season for temporal aggregation, and its implication for climate change impact assessments is underexplored. I further described the implication of arbitrarily selecting the season in this slide. So if there's a true season, selecting the wrong season basically represents a measurement error. Suppose the selected season is this period, and it includes both relevant and irrelevant weather realizations. If they are uncorrelated, it introduces classical measurement error and can attenuate the estimate. However, if they are correlated, it can introduce non-classical measurement error and bias the estimate in unknown direction. So in this case, we cannot even be confident that the estimates are either within a lower or upper bound of the true estimate. I describe this problem using this example. We collect state level monthly maximum temperature data in the United States over 1961 to 2004. Suppose the true season is winter, and the measurement error will be the difference between the true temperature data and temperature data aggregated over the selected season. So in this figure, the y-axis and the x-axis indicates the starting months and ending months of the selected season. For example, in this pixel, the starting month is January and the ending month is March. So the selected season will be winter. And the measurement error is because the selected season is the same as the true season, which is winter. So there is no measurement error. And the color in this figure indicates the correlation between the true temperature data and the measurement error. So in this pixel, the correlation is 0. However, if you look at the color of other pixels, you can see there are, if you select the wrong season, there will be the measurement error will be correlated with the true weather data, either negative correlation or positive correlation. So one lesson from this example is that arbitrarily selection of season can introduce non-classical measurement error. So in this paper, we study how arbitrary selection of season can affect the estimate of weather shock on agriculture. We provide a conceptual framework and use Monte Carlo simulation to study this question. To address this problem, we propose a grid search approach. In our conceptual framework, we formally define a set of possible seasons, which consist of 72 elements. So each element is consecutive months defined by a starting month and ending month in a year. Suppose the true season for the relevant weather condition is T star. However, the researcher select an arbitrary season T to aggregate the weather data. In reality, the true seasons is unknown. So the weather data are often aggregated by an arbitrarily selected season T, which introduce a measurement error. As we shown in our previous example, the measurement error are often correlated with the true weather data. So it means the measurement error is non-classical, and this can bias the estimate in either direction. In our paper, we further develop how the correlation between the measurement error and the true weather data can affect the direction, but we don't elaborate here. We propose a grid search approach to address this problem. The overall idea behind this approach is that a model based on weather data aggregated over the true season should fit better. So we identify the model with the best fitting season. Let me describe the steps very quickly. So we first aggregate the weather variables over all calendar periods, and we select a season and evaluate the goodness of fit of the model based on that season. Then we store the out of sample mean squared error for each model and repeat that for every season. Finally, we visualize the out of sample mean squared error and select the optimal season. We collect our weather data from the PRISM climate group at Oregon State University. The weather data include monthly minimum and maximum temperature and precipitation from 1963 to 2019 with a 4 kilometer spatial resolution. We also collect a state level panel of agriculture TFP data from the United States of Agriculture and Economic Research Service. Using the data, we conduct a Monte Carlo simulation. The overall idea of the simulation is to quantify the consequence of selecting the wrong season. So we evaluate the impact of uniform warming when the selected season is different from the generated that in the data generating process. We also want to evaluate how our proposed approach can recover the seasonality. So we derive the sampling distribution of the estimated seasonality in the simulation. Here is the setup of our simulation. We basically we have 5 types of true season, which are winter, spring, summer, fall, and annual. We have 4 types of weather variables, which are minimum, maximum, and average temperature and precipitation. We draw the state fixed effect from a uniform distribution, and we draw the error terms from a normal distribution. So based on these specifications, we generate the outcome variable y. Because our goal of the simulation is to study how selecting the wrong season will bias the estimate. So we derive the sampling distribution of the seasonality and the impact of uniform warming for all seasons. The estimation is as the following. So we choose with the selected season comes from the possible set, as we mentioned in our previous conceptual framework, which consists of 72 combinations within a year in total. And the weather variable in the estimation model, Z, may not match with the W in the data generating process. The reason is that we are also interested in characterizing the consequence of getting the weather variable wrong, besides of getting the season wrong. Here are the results of our simulation. In this figure, the true season is winter, and the y-axis and the x-axis again indicates the starting months and the ending months of the selected season. For example, in this pixel, the starting month is January and the ending month is March. So the selected season is winter, which is the same as the true season. The color in this figure indicates the percentage bias. The percentage bias is calculated as a ratio of the difference between the estimate using the selected season and using the true season to the estimate using the true season. So in this pixel, if you select the correct season, which is winter, there will be no bias. However, if you look at the color of other pixels in this figure, you can see that selecting the wrong season can either bias the estimate like in positive or negative direction. So we also did this for other type of weather variables. For example, the average temperature or minimum temperature, and also other types of true season, like the annual, fall, summer, and the spring. We summarize the findings in this figure. So basically, the bias are towards smaller impacts, which are indicated by blue in these figures. But there are also non-negligible cases where the bias are towards larger impact. Here are the results of season identification in our simulation. So this figure shows the sampling distribution of the identified seasonality. So the color indicates the number of times that our approach identified the season identified the season as the true season. So basically, the approach performed very well in identifying the true season. But there are some other chances that they misidentify. But the misidentified seasons are not very far away from the true seasons. So after our simulation, we apply our approach to a real world example where we separately estimate an econometric model for each USDA region. The outcome variable is the state level agriculture TFP growth rate, and the independent variable is the maximum temperature aggregated over a calendar period T in selected period T. Here are the results for the real world application. In this table, the first, it shows the impact of uniform 1 Celsius degree warming on agriculture TFP growth rate based on models with selected seasons. The first column indicates the result for using our estimate for the true season. The other columns indicates based on models using the arbitrarily selected season corresponding to winter, spring, summer, fall, and annual. We found that so if we use the model based on the optimal season we identified, we found a statistically significant effect on agriculture outcome, except for the Pacific Northwest region. Unsurprisingly, we find the effect mostly concentrate in the Midwest region, with an increase in 1 Celsius warming degree. The agriculture TFP growth rate will decrease by 4%. In this table, we also find that if you arbitrarily select a season to aggregate the weather data, it will bias the estimate in either direction. And this result is consistent with what we have found in our simulation. Here is the result for the season identification in the real world example. Interestingly, we find that the best feeding season in the Midwest region is from July to August, and this corresponds with the growing season in this region. So it provides some evidence that our approach can effectively identify the true season in a region. So let me conclude my presentation. So in this paper, we study how arbitrarily selection of a season to aggregate weather data can affect the estimation of climate change on agriculture. And we propose a research approach to address this problem. We collect weather data and agriculture TFP growth rate, and we apply a Monte Carlo simulation to study this question. We find that our approach is generally effective at recovering the underlying season in the data generating process. And also we find that if you select the incorrect season, you can bias the estimate in either direction. And the result is consistent with what we have shown in our conceptual framework. When we apply our approach to the real world example, we find that there are heterogeneous effects of temperature on agriculture TFP growth rate across regions in terms of direction and seasonality. Thank you. So please feel free to email me if you have any questions.
Great. Thank you, Zhiyun. So I think we have plenty of time for questions. So, either the panelists or folks in the audience can type in the Q&A any questions.
Oh, no question.
No.
Very surprised.
It's Sunday afternoon. I don't know. No questions? Okay, we have something. Zhiyun? Have a Q&A.
Oh, has there been any reductions in crop outputs? So yeah, so could you please explain a little bit about what is reductions in crop outputs? So yeah, yeah, it seems
It's not easy to clarify from the audience, because they cannot unmute themselves and explain. So, but I think they're asking whether you find some impacts or of climate change, and the paper is not really trying to answer that question. In a sense, is that's the point that he's making. Whether conditions have changed, have crop output changed as a result from that. So I think that if I may add, as you can clarify what the goal of the paper is, and it's trying to help people answer that question more rigorously. Really, is that what the paper is trying to do? Is come up with a way so that we choose weather conditions when we're dealing with aggregate measures like total factor productivity of GDP, right? When you have a Cornell study, you know exactly when farmers plant, when they harvest, when corn is flowering. But when you have an aggregate measure, what is a season? You have livestock. What is a growing season for dairy cows? Is not that obvious, and so there's no real guidance, as you said, Zhiyun, on how we should actually be imposing this. And many people, what they do is that they say, well, let's just do the whole year. Let's do January to December. And what you showed in one of your slides is that if you actually choose January to December, you actually get biases in either positive or negative, depending on the underlying seasonality. So it's actually a big deal to know exactly what the actual seasonality is, right? At least in the Monte Carlo results that you showed, right? Then obviously in the real life, we don't know what the season is, right? So, but at least we have at least one first step to try to go there. Mariah?
Yeah, thank you, Ariel. I just had a question about the different regions, and if you have any intuition or ideas for why the method may work sort of better in some regions versus others.
Good question. Zhiyun, that's for you. I'm your co-author, but I'm your backup.
Yeah, thank you for the question. So you're asking me about how region so is affecting the estimate.
Why can we find the seasonality, say, in the Midwest, and it's not as easy in other places, like in the figure you showed? I think that's the question.
Oh, so
slide 18, yeah.
Oh, yeah, I think that's a good question. So I guess the first reason may be the true data generating process. So for some region, in the data generating process, there may not be, for example, there may be only 1 month that is really affecting the affecting the growth of the crops. But for some regions, it is very clear that certain regions, certain seasonality is affecting the growth. So by nature, for some regions, it's hard to identify the seasonality. So I think our approach may not be able to identify the seasonality for some certain regions because of their data generating process.
And just to add to that, that there's there's some regions that might be much more diverse in terms of the types of crops. The Midwest is more homogeneous, and so you can see that it's kind of the middle of the summer that shows up, that kind of lights up in that grid search. And it's not surprising that it's like July is in there, because that's like when corn, soybeans are kind of blooming. But if you go to the Southwest, then it's a little bit more mixed. You can see, actually, if you look at the Southwest panel, that there's conditions in the spring, but also in the summer that matter. So there might be different windows, and the approach, as is currently being, we're currently proposing, it's only finding one season. So there might be 2 seasons, right? And so, we leave that for future work, right? So at least we're taking one step at a time.
Thank you.
Thanks. Zhiyun, another question? Still have a little bit of time.
Yeah, so I don't have a question, but I can see some recent research in the West using a region with diverse climates.
Yeah. So that's good. Yeah, people want guidance, you see. Okay, so great. So if we don't have more questions, then we can move so that we have more questions for general Q&A at the end. So
Okay,
so good. So let's do that. So thanks for the questions. Thanks, Zhiyun, for the presentation. And so now we're moving to our second presenter. So Simone Pirali is going to present from Massey University in New Zealand, is going to present a paper on the title here. Can you share your slides, Simone?
Is it showing here?
Yeah. Yes. Perfect.
Can you guys hear me, by the way, just to double check?
Yes, we can hear it perfectly. And then I'll just give you a heads up, at 22 minutes.
Yeah. Okay,
great.
Well, thank you very much for organizing this. And it's my pleasure to be here to show you this joint work with Kendon Bell and to talk about the historical impacts of weather on pastoral farm profits, and how this imply moderate to severe impacts of climate change on pastoral farm profits. And this is also a proof of concept start of work of a bigger project that will be starting in the next couple of months here at Massey and in New Zealand, financed by the Royal Society of New Zealand, together with Professor Chambers and Professor Ortiz-Bobea, where we'll look at also undesirable outputs, so the impacts of climate change on undesirable outputs. Okay, so the motivation of this work is that there is a quantification gap in Aotearoa, New Zealand. This quantification gaps is important because there are legislative requirements to develop national adaptation plans to climate change. And to do this, you need to somehow understand how much economic and social outcomes change due to climate change, and whether a specific adaptation action is worth the cost that is expected to have. So in other terms, we need to understand what are the monetary and non-monetary benefits of adaptation. And as I said before, there is yet not specific statistical quantification on a national representative sample of farmers. Moreover, some attempts have been done to look at the linear impacts of climate change and to linear impacts, of weather on agricultural outcomes, but no quantification of climate change impacts, and not on a representative sample, and not non-linear climate change impacts, which we are increasingly seen as very important. And we take as examples the dairy and sheep and beef sector in New Zealand, because the dairy and meat exports are very critical to New Zealand economy. They represent approximately 32% of New Zealand exports, and they are approximately 28 of the 87 billion NZ exports, dollars exports that have occurred in 2020. So they are really critical. To make a comparison, in the US, a dollar in New Zealand dollar is approximately 68 cents at the moment of a US dollar. So you'll be having around 19 billion US dollars every year are exported from New Zealand thanks to dairy and sheep and beef sector. So these are very important, and moreover, worldwide pastoral land accounts for 1/3 of global land use area, and between 7 and 10% of global caloric production. So it's very important topic. Okay, the specific research questions that we have for this particular contribution are: what is the historical relationship between local weather and dairy and sheep and beef farm profits and productivity? And what do these relationships suggest will happen to dairy and sheep and beef farm profits in the future due to climate change? And we'll talk more about profitability and productivity aspects in a second. Okay, so the data sources that we use for this are come from two sources. The first source is the NIWA Virtual Climate Station Network. NIWA is the National Institute for Weather and Atmospheric Research here in New Zealand. And this data set goes back to 1972, has daily observations of minimum and maximum temperature and calculated soil moisture. And we matched this data that are at 5 kilometers resolution to Statistics New Zealand confidential longitudinal business database, which is, as I said just a second ago, a confidential database on farm production. And we take from this database and from another couple of databases or matched databases from the Inland Revenue Department, the farm profits per hectare, and then we'll use in the future gross output and other types of inputs that are used on farm here in New Zealand. Okay, the climate projections data instead come from directly from NIWA, and these are downscale climate projections based on 6 global models from the coupled model intercomparison project number 5, and they are the downscaling is performed using local climate simulations, and we take for the moment we take 2 scenarios: a high climate change scenario or a representative concentration pathway 8.5, which as we all know is the increasing radiative forcing on pre-industrial level that would occur due to a pathway of emission that would occur up to the end of this century. And then a moderate climate change scenario, which is the so-called RCP 4.5, which instead has lower radiative forcing increase. And if you were to look at the increase in temperature, the first one would imply approximately a +4 degrees Celsius increase over pre-industrial levels, and the other one are 2 to 3 increase in degrees Celsius over pre-industrial levels. Okay, so some a peek to the summary statistics of the farm production data from Stats New Zealand. We use operating profit, and operating profit is of the dairy and sheep and beef farms. Operating profit is the difference between revenue and operating expenses. And we have a sample of approximately 70,000 farmers, 70,000 observations, but there are approximately 10,000 farms. So approximately it's 7 observations for each farm in the data set. And the period of observation is between 2002 and 2018. All right, so the statistical model that we use is a regression model that has farm fixed effects, alpha I, that control for average farm performance. And then we have gamma T RI, which are regional time fixed effects. So these control for regional effects in each year that may be things like shortages in inputs in a certain region that increase, for example, prices for inputs in a certain region in a certain year. And then we have the rest instead is soil moisture and temperature variables that find the nonlinear effect of remaining soil moisture and temperature variation on profit per hectare. And we include, as you can see from the lagged variable here, we include up to L, up to 3 years before the profits are reported, okay, in the data. So that would mean the first year during the time, during the same year in which the profits are reported, and then up to 2 years before. Okay, and this is critical, as we'll see in the results, to show the dependence of pastoral farm profits on previous years. And for example, because of the building of the body mass of beef cattle in previous years with respect to when they are actually sold. Okay, so if we compare, we're comparing here, for example, farms within a region. This is the region of Waikato, which is a very important farming region in New Zealand, and it is a very important dairy farming region in New Zealand. So we take 2 farms, Farm 1 and Farm 2, and this is an exemplary, as an example in a sense. And we take, for example, the data as you see them at first glance, and you would see that Farm 1 has higher soil moisture than Farm 2. However, Farm 2 has higher profits than Farm 1. Okay, so one would think potentially there is a negative relationship between these variables. However, if we take away the average farm effects, which is what we do in this statistical model that account for better management, we already see a different level in the data. And then if we take away also average time effects, in this case we're taking away the same effect in both farms because they are in the same region in every year, then we see that in fact there is potentially a positive relationship instead between soil moisture and profits. And that's actually what we see in our results. So in the main results show clearly a negative effects of dry soils, okay, but a positive relationship between moisture and profits, okay. And so if we look at the dairy case, and we take these are marginal changes with respect to a day at 20 millimeter soil moisture deficit, and if we take a change in a day between 20 millimeters soil moisture deficit and 140, which will represent a very strong drought, a day of change would imply a decrease in operating profit of approximately $4.59. And that $4.59 compares to a 4.42 mean daily operating profit in the 2016 to 2018 year average. So that in a sense says that if you change a day from a relatively wet condition to a very dry condition, you lose slightly more than a day of operating profit. On the other hand, if you look at the sheep and beef case, at the sheep and beef sector, we see that if you change again the conditions for a day at 20 millimeters soil moisture deficit to 140 millimeters of soil moisture deficit in the same year, you only have approximately 34 cents of drop in profits. However, if we include also the previous year weather, okay, we see that that has a 98 cents drop in operating profit. So if the combined effect in a sense of the weather both in the same year and the previous year has again almost a day, 1 day of operating profit, and that is $1.32 of drop from a relatively moist condition. If we look, so we don't see very strong, clear effects with respect to temperature, with respect to the dairy farms. But if we look at the sheep and beef case instead, we see quite strong, even though uncertain effects of temperature on sheep and beef farm profits. And in this case, we see that there are quite strong negative temperature effects, even though uncertain, especially if we look at increases from 20 degrees Celsius to 25. We receive a drop of approximately 290% in profits. Okay, and that drop, by the way, is balanced by an increase in heat from approximately, for example, if you take 8 degrees Celsius to 20, so if you were to increase the exposure of the average farm to more heat from 8 to 20 degrees, you would have an increase in profits of approximately 153%. So this, in a sense, balance out, in part at least. And from these are the historical impacts. But if we look at the future, as we said, we have this couple modeling intercomparison project downscaled to the New Zealand case, and we obtain these projected changes in future dairy and sheep and beef profits. If we look at the projected changes only due to moisture changes, we see that the taxable profit at the end of the century is approximately 20% less than in the year in the average between in 2016-2018, and for dairy. This also compares. This is the stronger climate change scenario. So the RCP 8.5. If we look at the RCP 4.5, instead, that has approximately a half of the drop. Okay, in profit. If we look at the sheep and beef sector, well, the sheep and beef sector has a taxable profit in 2100 of approximately 7% less than at present. Okay, and again, these profits are approximately double. This drop in profits is approximately double with respect to the RCP 4.5. However, if we consider also the temperature changes for the sheep and beef sector, we see that in fact the temperature adds a lot of negative effects to the soil moisture changes in the case of sheep and beef on the sheep and beef sector. And in particular, we estimate to have approximately a drop in taxable profit of around 54% with respect to present profits. Okay, and one other thing, we can see also that these changes are very, in a sense, very uncertain. Okay, and this uncertainty, there is almost, these are the 95% confidence intervals. So there is a high probability of a loss, in a sense, in 2100, but of course there is a wide range of possibilities there. Okay, and this we are trying to understand better why this happens, and we'll have more, hopefully more answers in the future. Okay, just some implications of these results, where we think that these results can be used to understand and quantify the drought impacts and help in design drought support in the future. We think that these results can also be used to value the benefits of adaptation. So, for example, if you were to think of building a new dam to irrigate cropland and pasture land, where you could, in a sense, balance that, compare that cost with the expected net damages from climate change, and see whether that cost is actually justifiable or not. Moreover, in the future, there could be potential for pricing weather indexed insurance. And so we think that these results could also be used in that sense. Finally, some points to conclude. Well, the results support for now, and we have, I'm gonna say something more in a second about future work, but these results support the conclusion that avoiding the worst climate change will pay dividends to Aotearoa farmers, to New Zealand farmers, and potentially there could be severe losses that could be avoided if temperature has indeed the large effects that we estimate at the moment. Some words of caution are that well, first of all, the benefits of adaptation are in a sense moderate to high, okay, but so if we include in these estimates, because we do not include the costs that the farms have incurred in the past to actually have some of this insurance against bad weather, we include the benefits of this adaptation in these estimates, but we do not actually include the costs that these farms have incurred over the years. And so really we will be, and we are already working on refined estimates of this data, of this work, including other aspects like capital costs and other inputs, okay, fertilizer and other potential inputs, and also directly yield production from so not profits but actual product. Okay, and another word of caution is that potentially the RCP 8.5 is actually probably won't happen, is one of the most extreme climate change scenario, but in fact it actually might happen. And there are recently there have been also increasing in a sense evidence that potentially some of the climate change models are actually underestimating the productivity on the higher tail of the productivity spectrum, and that would mean also that there would be higher emissions as well. And so potentially that we could actually have approximately 35% chance of actually going beyond the RCP 8.5 scenario. And moreover, we have included, yes, thank you, Ariel. We have we do not include price changes in this work, but actually potentially climate change will affect prices as well. So potentially we would have an increase in prices of agricultural products that could balance out these losses. And so that is something that we potentially have we have to do in the future. Well, thank you very much for your attention, and I'm here to listen to your comments and your questions.
Great. Thank you, Simone. So for the audience, you can write your questions in the Q&A. We as a panelist cannot write questions in the Q&A. That's like a weird Zoom thing. So if you are not asking questions, we can just here unmute ourselves for the panelists and then just ask questions. And then we'll give priority to the Q&A from the audience as they come in.
Yeah.
So I'll start with the first one then, Simone. So you include weather from lag weather, right? From this year and then a few years back, and I think it makes sense in the sense that it's not an annual thing. But what part of the year did you include? So this is relating to Zhiyun's presentation. Exactly, like, is it the whole year? Is it?
Yeah, at the moment is the whole year. Yes.
Okay.
And in fact, we have well in this project that we'll be hopefully doing together. We have included the chance that we can refine the timing of the season, and at the same time also the spatial aggregation the spatial aggregation at the moment is 5 kilometers. So we only know in 5 kilometers what happens in that 5 kilometers square, but we know the even more exact location of some of the farms, so we could potentially go even further in precision in the spatial aggregation. And as you said very correctly, at the moment this includes the whole year, but there are some in a sense some events that are more important to pastoral farming, even though pastoral farming and pasture these are pasture grazing systems. So the pasture grazing systems are relying 365 or 366 days a year on weather, more or less, apart from irrigation and apart from drainage for the opposite. Now, if you have too much moisture, you would have drainage systems that here in New Zealand are quite present as well, to not have pugging, not to destroy the pastures. But at this moment, instead, there are the whole year is included, and some droughts, for example, are more like, in a sense, they are worse on pastoral farm profits, depending on the timing in which they come. So drought, for example, in during the strong lactating season on a dairy farm may be much worse than later on in the summer. And so
Okay,
that, for
'cause-
example, early
Yeah.
spring or spring, a spring drought would be worse than a late summer one.
Okay.
And so that really depends. And we're planning to do this in future work.
Yeah, because I anticipate that the season thing is gonna come up, you know,
Yeah.
and you can find, you know, so the sensitivity analysis would be
Definitely.
nice. Other questions? I have more. I have a bunch of questions. So, you know, I can just keep going.
That's good. Let's see if.
Yeah. So one other, you know, if please interrupt me. Otherwise, I'll just keep shooting. So you include a region by year fixed effect in your model, right? And in my experience, weather is highly spatially dependent. You know, in particularly in the U.S. and the Eastern U.S., you know, but in New Zealand. So I'm wondering how much, when you do that, you wipe out a lot of the variation. You know, over time, right? Because it's a little bit aggressive to do that. So there's this discussion in you know, when the Shannon Greenstone wrote the paper in the AR, and then you had the comment by Wolfram Schlenker and colleagues. One of the points that they made is that they included a state by year fixed effect in their regression, and that wipes out so much that you're basically, if there's some measurement error in the weather data, what you have, you're kind of amplifying the noise there, that you know, that there's not a lot, there's not a lot of within state year variation left. So I wonder if you did different levels of fixed effects to see how the results change, and if you get a bigger magnitude as you have more, because people worry more about the location, you know, the time invariant omitted variables more than the time varying ones. So, you know, it seems like it maybe it's something a little bit more conservative, you know, more I'd say less aggressive might be interesting to see.
Yeah, absolutely. Yeah, I think you have a very good point there, and we were trying to somehow, we're trying different levels of fixed effects. We didn't have the time to get more results out, because this is a confidential workspace, and we need to have time to output check what comes out of our results. And so we have more results coming out with different levels of fixed effects as well. And for sure, there is still a lot of weather variation in this case, because the regions are quite wide. The regions that are that we have considered are quite wide, while and there is a lot of variability in weather with respect to where these farms are. So there is still a lot of weather variation, apart from the if you consider instead of a state and a county level effects.
Okay, there's a last question in the Q&A, and then we move. We have a little bit more time because Zhiyun's presentation was a little bit shorter.
Yeah.
So if you can answer that, and then we move to Mariah's.
Hi, Doug. Thank you for your question. The question says, is there any discussion of biologically changing the livestock to withstand lower grass feed? Yes, absolutely. There is a lot of discussion about a variety of potential solutions to climate change. Some of them are to have the same grass feed, but less methane coming out of the burping of the cows, for example, or having different types of feed, different types of ryegrass, of grass, different mixes. There are also methane inhibitors that, as we know, that the methane is created by a set of bacteria in the rumen of the ruminants, which are called archaea. And there are some scientists that are looking at either inoculating vaccines against these bacteria, or inhibiting these bacteria with pills. So in the case of New Zealand, the
we'll
first
have to move, Simone. I hate to interrupt you, but like I don't want to eat up too much on the time.
Let me, I will just finish the sentence, and so there are a variety of different ways to solve this issue. Okay. And there is a lot of work done by Ag Research in New Zealand, which is one of the current research institutes. Thank you.
Okay.
Sorry about.
No, and Tim, and I'll send you some questions offline through via email, and then I encourage the audience also to do that with every presenter. So now we move to our last but not least presentation. So Mariah Bostian from Lewis and Clark is here with actually her co-authors, some of her co-authors here. So the time is yours, Mariah. So feel free to start. I cannot hear you.
Sorry, I muted myself and then somehow took down my slides.
Good.
There we go. Okay. Thanks, Ariel. So this is joint work, and I think most of the co-authors are here. And we take a productivity theoretical approach to measuring adaptation in this paper, both in terms of production efficiency, as well as the production technology with application to agriculture. And then we're also interested in incorporating environmental objectives into measures of adaptation. And so we also include a model of nitrogen loading as part of this framework. So this is in response to increasing attention to adaptation, both in research and policy. Most recently, we've seen a number of new directives coming from the Biden administration to government agencies to target resources to adaptation and practices to adaptation, including the USDA. In the literature, there's been a shift really from looking at shorter term weather fluctuations to longer term climate change and the effects on production. And then in the productivity literature, more specifically, there have been a number of recent studies to incorporate measures of climate change into estimates of the production technology. And that's really where we fall in this study. And then across these studies, in general, the findings have been negative for US agriculture in recent decades in looking at climate effects on productivity. Okay, so then, turning to the productivity literature, most of the existing measures that we have for adaptation are in terms of efficiency change relative to a weather or climate adjusted frontier. And so in this study, we're also interested in technology change and how changing climate conditions may be shifting the production technology, and that part of that shift in the technology could also be interpreted as a form of adaptation. So rather than just looking at the efficiency change component. And so we use a Leuenberger productivity indicator that allows us to decompose overall productivity into these two effects of efficiency change and technology change. And then our adaptation indicator simply takes the difference. And so this gives somewhat of a D&D interpretation to the indicator value because productivity is a measure of change over time in outputs relative to inputs. And so we're measuring how that change is affected by changing climate conditions. And so then we can decompose into these separate aspects as well of efficiency and technology change. And then we also incorporate a BAD, nitrogen loading in this case. And this is a form of pollution that is also affected by climate change. So I think it's one that's particularly relevant for thinking about adaptation. Then we apply the framework to production in the Mississippi River Basin for 1987 to 2012. So just to preview the main results, we find overall productivity gains driven mainly by technical progress And this is consistent with a number of previous studies in the region. We also find some modest adaptation gains using the indicator. And these are driven both by, we find driven both by adaptation efficiency as well as technological progress. And then we find that the gains are most concentrated in the upper Midwest and lower South regions of the basin, where more of the losses are concentrated in the central and the eastern regions. So we're also interested in the spatial distribution. So this is a look at changing climate in the basin from 1990 to 2010. This is a map of percent changes to temperature, and temperature in terms of the 30-year climate normals. And this is also for the growing season months from April to August, just for reference. So we see that temperature is increasing over most of the basin to a varying extent, most so in these upper Midwest regions and then moving into the eastern regions of the basin. And then looking at precipitation, we see the Midwestern, central into the eastern regions seeing increases to precipitation over the study period, whereas the uppermost Midwestern regions and then the lower South, we see decreases. And these again are for the growing season months. Okay. So to incorporate these climate conditions into the production technology, we consider two alternative production technologies, one with climate and one without. And we refer to these as meta technologies here because in this case, we are not allowing for any technical regress. So we assume that production that was possible in previous time periods for a given set of climate conditions is still possible today or in current time periods. And then in terms of notation, we let X represent the production inputs, Y the intended production output, U is the unintended or undesirable, in this case, nitrogen loading, and then our climate conditions represented by W, which we also incorporate as inputs into the production technology. So to illustrate what we mean by technology change with and without climate, so this illustrates four separate frontiers. The two solid frontiers are the technologies for time period T, and then the dotted frontiers represent future technologies in T+1. And then I'm just to borrow some phrasing from Chris O'Donnell, I'll refer to the climate adjusted frontiers as the climate specific frontiers. So these represent the technology for the climate specific to a given location. These outer frontiers we think of as the period specific frontiers or technologies that are the technology for all climate conditions. And so looking at the figure, we see that both technologies are expanding. So we have technical progress in both cases. However, the increase to the technology for the climate specific case is less than the increase for the period specific. And so in our framework, we take the difference of those two changes to measure adaptation. And so we would interpret this as a negative form of technical adaptation, that the climate specific technology is expanding by less than the period specific technology. And then the other aspect to this is efficiency, which we measure in terms of distance to the frontiers. And so in time T, if we let this represent observed production in time T versus time T+1, we see that efficiency is deteriorating or inefficiency is increasing over time. We're moving further from the respective frontiers. But if we look at the climate specific versus the period specific, in this figure, the increase to inefficiency is greater for the period specific than it is for the climate specific. And so our framework would interpret this as some adaptive efficiency gain, that we're doing better relative to the climate specific frontier than we are relative to the period specific frontier. So that's just to give some intuition for this idea of sort of taking the difference to measure adaptation. So this is for just intended output, but we're also interested in unintended, undesirable outputs. And so to look at both the goods and the bads jointly, we estimate the output set for both goods and bads. And so I have the corresponding output sets here with and without climate. And then to mathematically represent these output sets, we use the directional output distance function, which measures the joint feasible expansion of the intended output and then contraction of the unintended output, moving in a given direction, G here, which specifies that direction of expansion and contraction. And we use a unit directional vector in our case, which facilitates aggregation to apply a common direction across units for thinking about aggregating these measures over space and over time. And then to interpret the values of distance. So a distance equal to 0 would imply that we're at the frontier and it's not possible to expand or contract further. And then distance increases with inefficiency. So the higher the distance value, the more inefficient we are for a given point in time. Okay, and so then to illustrate these directional distance functions and the output set for goods and bads, expanding the good, contracting the bad, moving in the direction G. And then the interpretation is the same in terms of the climate specific technologies versus the period specific, just looking at the output orientation instead. So then these distance functions are used to construct the overall Leuenberger productivity indicator. And this is the main equation for the Leuenberger. And just to give some intuition for it, it takes the average of the change in an efficiency relative to the time t+1 frontier versus the time t frontier for observed production in time t versus time t+1. And then we include the full decomposition in the paper, but this can be decomposed into separate measures of efficiency change and technology change. And the main thing to keep in mind is that overall productivity is the sum of efficiency change plus technology change. So this is an additive measure of productivity, which also then facilitates taking the differences to focus on adaptation. So the adaptation indicator simply takes the difference in these productivity values estimated with and without changing climate conditions. And then this difference can then be further decomposed into the efficiency change component to adaptation versus the technology change component to adaptation. And then to interpret these values, and I think in some sense, I think this is intuitive in that a negative adaptation value would imply that your productivity gains relative to the climate specific frontier are less or lower than your productivity gains relative to the period specific frontier. And then the same interpretation holds for both the efficiency and technology components as well. And then finally, to focus on longer term climate conditions, rather than looking at sort of year-on-year changes, we focus on 3 separate climate periods, and this is following Burke and Emmerich somewhat. We work with 1990, 2000, and 2010 as our 3 climate periods, and then we construct 5-year windows around each of those periods. And this is driven, largely by the timing of the Census of Agriculture. But we take the average production values from the census for each of our climate periods and use those in the technology estimation. We also use the average nitrogen loading values for each of these 5-year windows for estimations. And then we use the 30-year climate normals for each of the climate periods. Okay, and so we apply the framework to the Mississippi River Basin. We restrict to areas east of the 100th meridian, similar to previous studies as well. And we refer to this as the EMRB. We work with county level Census of Agriculture data for aggregate sales and expenditures from 1987 to 2012. And then we match these to nitrogen loading estimates that were conducted annually for all of the subbasins in the lower 48 states, also extending from 1987 to 2012. And then we also draw our climate data from PRISM, and we draw for the years 1950 to 2010. We take the monthly values for those years, and then we focus on the growing season months in particular to construct the 30-year climate normals. And then we use GIS to match all of these to the county and annual level. And then finally, we use non-parametric linear programming methods known as data development analysis, or DEA, to estimate all of the underlying distance functions to construct the productivity indicators. So this allows us to avoid making any functional form assumptions on the distance functions, and relatively straightforward to implement. Okay, so production in the basin over the study period. So this is a map of the sales to expenditure ratio, percent change terms from 1990 to 2010. So we see some considerable gains over much of the basin, particularly in the Midwest and upper Midwestern regions. We also see increases to nitrogen loading during the same time period and in largely the same regions of the basin, particularly in the Midwest, and then extending down into the sort of upper South as well. And then to incorporate climate, we follow Wang et al. And construct two separate weather indices for agriculture. We use the ORI aridity index for crop production, and then we also construct a temperature humidity index, or THI, that measures heat stress to livestock. So I've included those formulas here. So for the ORI, we restrict to the growing season months from April to August. For the THI, we use the annual monthly averages of those values. And then we work with all of these in our models in terms of their 30-year climate normals. So just a quick overview of the data. For the production variables, we see acreages relatively stable, sales and expenditures both increasing, temperature and precipitation increasing somewhat as well. The ORI index value falls somewhat, but that actually indicates an increase to aridity over time. And then the THI increases somewhat as well, indicating some increases to heat stress. And then we see increases to nitrogen, and those nitrogen levels are peaking in the 2000 climate period. So the inefficiency results, these are the distance values, average values for each of the climate periods across 4 separate models. So we estimate the technology with and without climate. And then we also estimate one version where we only consider production objectives, and a second where we also consider the environmental nitrogen loading objective. And these values can be interpreted as percent of sample mean. So these are potential increases to outputs, decreases to nitrogen loading as a percent of sample mean values. So you can take a hypothetical observation at the mean, and this would imply that this observation could increase their output by roughly 29%, just for interpretation. So these values we see increasing over time, and that's really the case across models. The nitrogen inefficiency peaks in the 2000 period, which is also when nitrogen levels peaked, so that's not surprising. And then for the production only objective, we see the highest inefficiencies occurring in the final 2010 period. So we use these distance models to construct the Lewinberger productivity indicators. So these are the indicator results. The main results here are that we see, in the first half of the table, we see productivity gains across models and increasing over time, and that these gains are driven by technology gains outweighing efficiency losses through time. And this really holds in the majority of cases. And this is also consistent with previous findings in the literature. And then if we compare the with and without aspect of this for climate, in this case, we see slightly higher gains on average relative to the climate specific technology than to the period specific technology. And so then this yields a net positive adaptation indicator value in each case. And these differences are, I think, relatively modest, ranging from 1.2 to 2.8% differences on average. And we don't see the same clear story as before, where, in some cases, this difference results from efficiency gains relative to the climate specific technology outweighing some technical loss. But in others, we see the opposite. So it's not quite as clear as in the productivity results above. But these are all the average values. And then I think it's really interesting to look at the distribution of these over space and sort of be able to get a sense some of the differences in magnitude as well. So, where are the gains and losses concentrated in the basin for adaptation? We see the gains concentrated mainly in this sort of upper Midwestern portion of the basin, and then also some in the mid to lower South. And then the losses more so in the center and eastern regions of the basin. This is for the production only model. And then when we move to the nitrogen loading model, the pattern is similar, but there's a bit more dispersion here than before. So to wrap up, we've developed a new indicator for adaptation to measure adaptation both in terms of efficiency and technology components. And this is based on the Leuenberger productivity indicator. So it's grounded in economic index theory, but then I think it has sort of a relatively simple, intuitive interpretation and thinking about taking the difference with and without changing climate conditions. We also construct a new data set that matches historical production to both climate and nitrogen loading, which I would like to exploit more. And then I won't go through the main findings again, but we should note that we limit this analysis to, it's highly aggregated. We're working with county level aggregate sales and expenditures. And so we're not really able to look in more detail at specific practices that producers are implementing in response to climate. And so I think this would be another area to extend in the future, and particularly to work with more detailed production data and possibly kind of further decompose this adaptation indicator into other components like mix and scale as well, that would give us some sense of that. And then, extending to more recent years, and then also looking at the West, I think would be another future, just given sort of the changes that we see happening in this part of the country. So I'll stop there. Thank you.
Great, thank you, Mariah, for interesting presentation. So we already have a question lined up. Doug Reno is asking about carbon fertilization.
Okay, thanks, Doug. So Doug's question is, does carbon in the air help or hurt? Does more carbon make crops grow more productive or cause more weeds to grow? So we don't include any measures of carbon in this model, but I think that would be another area really to extend to. And just from working with other projects that have used integrated models that, particularly for nitrogen loading, I know in many cases it's possible to also incorporate a carbon component to that. And I think it would be really interesting to include, but we don't consider that. We don't have it in the data at all here.
Great, thanks. Any questions from the panelists? So I have a question then. So Mariah, so one question that I have is there a way to determine how small changes in the modeling assumptions that you make about say the seasonality or the type of weather variables, like how dramatic does that, how much does that matter to your results? Is that something that you've done, like a sensitivity analysis of that sort?
Yeah, I guess we've so far in a more of a almost ad hoc way, in that we've estimated this a few different ways now, and earlier versions included temperature and precipitation and growing degree days in earlier versions as well. I think the bigger change that we've made compared to previous iterations of this is moving from these sort of year-on-year technologies to using a meta technology framework. So, in terms of where have our results really changed the most, I think that's where we've seen more change. And in fact, I think we've kind of found more evidence of adaptive gains once we've moved to this meta technology assumption rather than the year-on-year technologies.
Okay, but is there, a follow-up is that, is there any criteria that you could use to guide your the way that you build the model, for the weather, choosing the different weather variables or things like that? Is that because, I'm thinking, similar to what, say, Zhiyun was doing, is that there's some weather variables that fit very well out of sample, right, and others that don't.
Yeah.
And when they don't fit very well, you get very small effects on everything. Then when you get variables that match very sensitive periods, then you get huge effects. And so I think, I'm curious whether in this framework there's a way to try to sort of get a sense of how something to guide model building.
I guess it's not, I haven't really thought very much about that specific question and sort of choosing. I think I've relied a lot on previous studies to sort of select, kind of constructing these indices versus using raw temperature and precipitation. But no, I think it's a really good question, especially after seeing Zhiyun present earlier too, just in thinking about, are we really including the best measure of climate? So like, for instance, the annual value of the THI for the measure of heat stress to livestock. And I'm not sure that annual is really where we're going to see the heat stress effect occur. So no, I don't have I guess I don't have an immediate answer to your question, but I think it is an important one.
Other questions? I think we have a few minutes. Yeah, about 3 minutes. I have more. I'll Simona, you have your
let me ask just a clarifying question. Very good. I think it's very good work and very interesting. And I would like to ask if the meta technology you mentioned, is it you mean enveloping the data points sequentially?
Yeah,
or,
it's a cumulative. It's a cumulative meta
Okay.
technology.
Thank you.
So it just
that makes
builds.
sense.
Yeah.
Makes sense. Thank you very much. Sorry.
Yeah, no, thank you. And that, the shift to that is based on some earlier comments we've gotten in presenting this work before, just in, the importance to not allow for technical regress in this case. And
absolutely.
Thank you.
Yeah.
And another question, if there's no one in queue, is, so you use the census years, right? You use data from the census, right? And so that's every 5 years. And the data reported is from that year, right? Or the previous year, I forget exactly how. So the 2012 census is, reflects conditions of the 2012 year.
Yeah, exactly.
But it sounded like the weather variables that you account don't really match that year. So I'm trying to see how that how that it's coming together, because the census
Yeah.
doesn't tell you average conditions over the past 5 years.
doesn't.
It just tells you
No,
snapshots,
exactly.
right? So how does
Yeah.
that? Can you clarify
Yeah,
how
well,
does
I
this
guess
work?
the way we're trying to sort of get around that sum is by working. So we sort of have 3 time periods: 90, 2000, and 2010. And so, for each of those, we average the surrounding census values. So like for 2010, the 2010 production values are the average of the 2007 and 2012.
Okay.
And then the climate variables are the 30-year normals for 2010.
Okay. So you're averaging the
Yeah.
census data. Okay.
So it's nothing sort of exactly matches in time, right?
Yeah.
And it's more these averages that overlap.
But there's also the 2017 data out, right?
There is, and we could, so the nitrogen loading data that we have,
is that USGS?
No, it's from a group at Stanford who they have a paper in Nature, and then I think I can't remember where the other one is, but they've created this data set of nitrogen going from 1987 to 2012. My understanding is that they're going to extend it, but as of now, I don't have it. Yeah. Okay,
good. So great. I think we're exactly at 30 minutes. So thanks, Mariah, for the presentation. Now we'll have a discussion with Spiro Stefano, who's the head of ERS. So thanks, Spiro, for coming on a Sunday afternoon to talk with us. So we're looking forward to your discussion.
Okay, let me see if I can pull my screen up here. I'm gonna just do this, see what happens. All right. Boop. Boop. Is that it? You see it?
Now, yes, we almost you can just press
put in presentation.
Yeah, in slideshow, and then we're good.
Excellent. Excellent. Okay. Well, very nice papers. One of the things that's impressive is the effort that all the authors have gone to build a data set to try to attack the question. And this is a theme that's on the top of everyone's mind from a policy point of view. At USDA, we have a Productivity Sustainability Council stood up now to look at this theme. It's on the front burner. At OECD, there's the Agricultural Total Factor Productivity Network that's taking the environment into account. In the EU, they're focused very strongly on sustainability in their farm accounting data network now. And so these are all right at the forefront. What is gonna knock on probably in the next couple of years is a trade story, because it's gonna span to trade. Trade where sustainability of production is going to be a main feature of emerging trade agreements. And so we'll see that component here also influencing the story. Right now, I want to kind of make a point that when we look at climate change and sustainability, agriculture is all part of this. It's a global, local challenge. We have local actions are going to be leading to global implications. Methodologically, what kind of modeling frameworks are we going to use? We had simulation frameworks starting off. We had an econometric framework follow, and with a non-parametric estimation framework, a non-statistically based framework. What kind of data are we going to be building? We're not taking all aspects of climate change into account. No one paper has done that. They're taking some core elements that the respective authors thought were important to include. And as was mentioned by already several questioning periods, which time scale should we use? How are we going to define the geographic boundaries of the pilot studies or the proof of concept studies? there's discussion here in terms of global implications of local action to policy and regulation. The mitigation issues that are on the table, but adaptation opportunities we see coming forward. And there's also a communication and engagement story here. We're talking about the data generators. You're getting data from at the farm level, the ag census, and whoever else is providing these databases and creating these databases at the micro level. We have the data aggregators that are present, and in all cases, we have to trust everybody. Trust is a core concept in folks contributing their information and how data are aggregated. And that's all part of the system that we need to kind of keep in mind if we're going to make some significant progress on this. So on the first paper, you take a global approach here. Okay? So you're addressing the performance of this grid search model across regions. Some challenges come up. How to deal with varying precision across regions. Some regions are more precise in estimation than others. It's not that we have to make those imprecise regions more precise. It's just we have to embrace that imprecision, right? Because that's signaling the diversity. Again, that came up in earlier questions. The diversity of what's going on in a region. The 3-degree centigrade change is, that's going to happen over a decade or decades, hopefully, right? And so adaptation and mitigation is going to follow, given the more gradual evolution of the temperature change. Product mix changes are going to happen. Innovation policy is going to develop and be an adaptation. There's a very nice effort by Alan Olmsted at UC Davis, economic historian, agricultural historian, and talked about charting how seed varieties actually were moving geographically, right, as a result of climate changes. And so there'll be that kind of adaptation. We've also already talked about what time scale to think about. So degree days was one, right? The clock does not start by our conventional clock time. How sensitive are our results to that, especially if you're getting down to these really local micro data that you're going to aggregate up. One last question then is, which map are you going to use? You used, in this paper, Zhiyun and Ariel, you used the USDA production region map. That's the map here on the left. 10 regions are in that study. Okay. We have lots of maps at USDA. I'm going to toss out another one, the farm resource regions. Here we have 9 regions. And so as an example, there's always one that I find pretty interesting. It's the fruitful rim. And that's, this area here, right? And it's diverse, huh? It's spanning coastal areas in South Carolina, Georgia, all of Florida, skims along the lower border of Texas, into Arizona and California. Arguably, California and Florida are the most diverse agricultural states in the country. So how do we deal with those? And of course, the fruitful rim does climb all the way up to Washington State. As an example, how does that kind of a resource map, farm using that kind of a map, play a role in starting to figure out, the diversity of some of your production results? Right? I don't know the answer, but these are assumptions that you can play with that could bear some interesting variation in what we have. The paper by Kendon Bell and Simone Pirali That's a local approach. That's great as a proof of concept. And one thing I've learned as an administrator, newly minted administrator, is don't use the word pilot study because everyone doesn't take that seriously. Use proof of concept. So as a proof of concept, a nice approach, you have great data. You've identified both soil and temperature as part of your story. Now you have these long-term projections that go out to 2100. Yeah, no one's going to believe that, right? But what is really of high interest is what's going to happen between now and 2040, right? And policy adaptation, you mentioned. Two great examples. Irrigation is one intervention that could help. And insurance as an indemnification. What type of insurance mechanisms can be brought to this challenge? Again, here's we always kind of think of some kind of innovation policy coming in to save the day, but there can be a market innovation here in terms of some kind of indemnification. Almost surely there'll have to be a policy support for that, whether it's a crop insurance or weather risk insurance. What other mitigation aspects can come, if you're looking at this 20-year window as part of a longer run window. And again, it's not meant to be critical of looking out 20 to 2100, but we can only look ahead so many time periods. And if we have a 20-year look ahead rule along a path that goes out to 100 years, we can get a better idea of what kind of policy implications. Challenge of doing the local approach is how to connect it to the global. And I know you folks in New Zealand probably think you're isolated from the rest of the world enough, and sometimes, God love you are. But these are challenges of taking these local approaches. So the productivity indicator approach for adaptation that Mariah and her colleagues have employed, they're teasing toward a global approach. Okay, what was pretty nice here is that while the prior papers take a political boundary approach to defining a map, you take a water-based approach, and water defining the boundaries. Here's you kind of explicitly step into the realm of water as an important aspect of agriculture. We look at our data and we look at what happens in agriculture. Water is everywhere, but in the data. And so kudos to your crew for focusing on that aspect of it. And the case study is great for looking at nitrogen loading in particular. This directional distance function approach, it's non-statistical in terms of variation in the data, has all the challenges of a non-parametric data envelope approach. We know these things. This adaptation indicator is a residual approach. It's looking at the difference in productivity with and without weather differences. That's what else is accounting for that residual? There could be lots of things going on in there. It's kind of like using a time trend to reflect technical change. That's just picking up everything that's correlated with time. That could be technology and everything else. I do appreciate the approach of taking those windows that you have, because you're looking at a very subtle effect, trying to tease out a weather impact, an adaptation impact. A year-to-year measurement is not going to tell you, a realistic story, but the 5-year windows can. So that's good. And so the question, comment on accounting for allocation changes. Again, this is the adaptation story of how are how our product mix is going to evolve over this time, and what are the items that are going to stimulate that movement. I was looking at those that data, those expenditure data that you had, and one of the things that was kind of interesting to see, here it is you had expenditures growing at a rate over that period of about 14%, and the farm producer price index is going up by quite a bit more than that. So about 40% was the increase between 1990 and 2010. That's from St. Louis Fed. So some adaptation, some mixing, some shifting of input use, of output mixes. How much of that is driving the adaptation story? So those are an interesting component. So you have productivity gains being driven by this, mysterious technical change that we have out there. You have adaptation efficiency is driving these gains. That would be really nice to try to break out in some fashion. What part of it is it? Is the adaptation at the producer level, the most micro level? Is it at the market, at the research level in terms of innovations in seeds and other products? These are stories, that are really important to tease out because they create lessons for everyone else. And if you go west, you're going to have a different kind of modeling frame to look at. So these are some pretty important pieces of work that have gone on. I'm quite impressed with the effort. I'm also impressed. Everyone starts thinking about a lot of the same issues in terms of timescales, maps, boundaries. How do they fit in? Our challenge was pretty easy. These are papers that focused on defined geographic regions like the United States, an island, New Zealand. Okay, what happens if we try to go to the EU? What happens if you try to go to Africa? The challenges magnify there. And so these are all things we need to be thinking about as we go forward. And there are going to be a lot more challenges pushing us as we go forward, especially as we start thinking of policymakers getting involved in a number of these things. So those are some of my thoughts. I really enjoyed presentations. And again, I want to emphasize the importance of the effort that was needed to build these databases. It's just like you just don't download it from one spot. It's about integrating and linking data across different platforms. This is the next wave of economic research in our area. Right? That is a necessary challenge, necessary activity to make this work. So with that, Ariel, I'm going to pass it back to you. Thank you very much for letting me participate.
Thank you so much, Spiro, for your comments and thoughts. And now we open up to general Q&A. So if the audience has any questions, please type them into the chat, into the Q&A window. And if the panelists have questions, then just unmute yourself and start shooting.
Well, I would just like to say thank you to everyone, and especially to Spiro Stefano for taking the time to do this comments to us, okay, and for the valuable comments, okay. And for sure also just to say that in New Zealand there is already quite a lot of irrigation being used, especially for dairy, and so potentially we see some of this effects in translating into not having negative effects from climate change in some cases. So we need to study more these issues for sure. Thank you very much, Spiro, for all of that.
So if I can lead with a question, and it's a question to Spiro, and one question that I have, and we have people in the audience, and then this is recorded, and so people will watch it later. And there's a lot of young people coming to these conferences, many ag economists thinking about these problems that are becoming more salient, and then people, and so my question to you is what would be your advice to young, or aspiring economists or young economists trying to do research that is policy relevant? It is easy to read a paper and think, oh, I can do a variation of this paper. And sometimes we are too academics are not necessarily thinking about policy, and then we just go behind, this new paper that changes a little bit what someone else did. And so, but that's not really necessarily a research that is thought from the get-go to think about policy. And so if you had any advice, that would be great. That's my question.
Well, sure. I'll offer my advice for what it's worth. First issue is focus on the relevant questions. Now, asking a good question is very hard. Einstein said once, if he had 1 hour to figure out the answer to a challenge and his life depended on it, he would spend 55 minutes thinking of the right question. The solution would then be pretty clear how to follow. So asking good questions and being able to execute on those questions and be expansive in terms of looking at the resources available to you. As I mentioned before, the data that are available. Start thinking about what kind of data can we marshal to the effort. When I was a graduate student, the kind of data that we had were almost always national, highly aggregated, maybe state level data. Micro level data were pretty rare. Everyone realized the importance of it, and the community responded. So focus on what are the relevant questions. Look at the real world. Right? Your set of interesting issues to explore are not just in the journals. Sometimes the journals are kind of like the law. The law is not about justice, it's about precedent. The journals expanding, taking the next step, it's about precedent. Can I, as you mentioned, take the next step to tweak? Look to differentiate your work from what is out there. Product differentiation is the key mantra for economists. It's not innovate or die, it's differentiate or die. And then the best way to try to make connections, to add value, is to take different streams of work and pull them together. This is not just a climate change story. Okay? It's also an open competitive market story. It's also a story about trade. It's also a story about equity. Pick two of those, pull them together, pull those streams together. Then you're going to add a lot more value, a lot more interest from the policy community. I'll stop there.
Yeah. Thank you for the wise words. Thank you. So we have a question from the audience. So Doug Reyna is asking a question about EV or ET, I guess, electric tractors, and how's that gonna play out? Can you see the question there? If we use, yeah. That's for everyone, I guess, or is that, I don't know if it was intended to anyone.
Well, I'll jump in on this. The labor-intensive aspect of it is, this is probably one of the biggest challenges we have in agriculture, is the labor story, and part of it's a policy-driven challenge, and part of it's just what are opportunities in other sectors, and so lots of innovations that are going on in agriculture are looking to be labor saving. I'm not familiar with electric tractors in particular. I'm not clear on how that would be labor intensive with the electric tractors. I know that a lot of mechanization efforts are going on right now. One of the biggest labor challenges in agriculture are just in specialty crops, fruits and vegetables and such. But I'm not familiar with any electric tractor technology that would be kind of addressing this question.
I think there was a column recently about they could work close to farmerless farms. I think so. Food for thought there, I guess. Any other questions? We still have 4 minutes to really take up all our time. And I'm sure we have something always in the back of our head that we want to ask here.
I'm going to just make a plug here. So Ariel and Zhiyun's paper looked at, depended on state level data that ended in 2004. So at the Economic Research Service, we have been actively re-engaging that work to update the state level accounts. So
Awesome.
that will be coming. We have work that we've been focusing on water and survey of irrigation organizations. A couple of reports came out just recently. So we have a lot of data that will be available to the community there. And NASA is working on getting some climate relevant surveys for agriculture stood up and putting those out in the field. So we're reacting, we're trying to contribute. And if you know anything about USDA's research capacity and us at Economic Research Service, we are incredibly data driven. We live, breathe, and eat data. And so that's how we depend on the work we do. So we're trying to respond, and folks have interest in trying to use our data. We are more than welcome to help you access it. And the whole system, really, federal statistical system, is looking to be much more open and making data available to everybody. And so you'll be hearing about that. You probably heard about that at these meetings in the earlier session, but you'll be seeing and hearing more and more about that in the near future.
Great news. So one question is here. Now you talk about data. You open the you open the door. So one question that I have is about the census of ag, right? Because the census of ag is collected at the farm level, and as researchers that are outside the government, we only get county level data, like the one that Mariah was using. Researchers can use census data, even micro, so the micro files, but the USDA, the ag data, it feels like farmers are have a higher protection than U.S. citizens in the terms of how well guarded their data is. But there's standards at the federal level on how to use these data. So I wonder, is there because it would be of tremendous value to be able to link over years census data from farmers to understand how they respond to a bunch of different shocks. And yeah, I think that I think there would be like a boon, so much research that would be unleashed, if micro level data, like the Europeans have the FADN data. But in the U.S. side, there's survey data, with the arms. So I'm thinking there's a richness in the census data. Can we be hopeful about that?
I don't know the answer to that. That's a good question, right? If you want to go to longitudinal research database, for example, like version that Simone used in New Zealand. Yeah, you can get the establishment level data, plant level data, finer than the firm level data. I'll ask my colleagues over at NAS about what is the history of that. I'm not going to speak to what will become available, but I'll check on it for you and get back to you.
A boom on research, very extremely high quality research, from ag economists coming out if we had data like that. That our health economy, our health people, and there's so many people how we can't. So we're officially out of time. If there's a last question, I think we can probably squeeze it in, but otherwise, it's been a great session, and thank you, Spiro, for making and everyone to be here and people in the audience. Also, thank you for being here. And if you're watching, I hope you enjoyed the session. If you're watching the recording.
Very much, and we're looking forward with the next iterations of work of everyone.
Yeah.
And hopefully also ours.
Hopefully in person.
Yeah.